welcome to this evening to our new conference call with Alan, who joined us today for another talk. And I'm really happy to have him back again. For those who visited and joined us at previous webinars, you've seen that Alan was also part of the story last year. And I'm just happy and thankful that he's back. So today we have this very specific topic. It's also quite a research-focused one, which I like. It's about from massive label data to few-shot learning in NLP. I like that subject. It's awesome. Alan, when we discussed it last year, I was very attracted by this idea of few-shot learning. And actually, when we handed over that kind of research idea in August, we also discussed what it really means if you work with small data. So welcome back to you. What are you doing on your daily basis for all those who haven't seen you before?
Yeah, first of all, thanks for inviting me. Can you hear me well?
It's pretty cool.
Yes. Yeah. So yeah, thanks very much. Yeah. So I'm professor of machine learning at the Humboldt University Berlin, and there I do mostly research on natural language processing, with also a strong framework development component, because at my institute, together with the open source community, we also developed the Flair framework, meaning that all the research that we do sooner or later finds its way into the Flair framework.
Sounds awesome. I will start a poll, by the way, so don't be confused if I'm just sending you the questions at the moment. Vitas, you have something you want to tell? You're raising your hand. Anything a problem? Was a problem, Vitas?
So at least on my system, you're a little bit quiet, Stefan. So I don't know if you can...
Quiet, so I have to speak up. It's easier now.
I'm not sure. So, but maybe it's just my computer.
Okay, I try to speak up. I hope you can hear me quite well. At least, Alan, I can hear you perfectly. So that's the most important part, right? So I started the poll, as you might have seen. So that's already running. I usually ask, what kind of profession do you have? What's your level of expertise? Which helps us a little bit to adjust the talk and to have a look at what your interests are, basically. So this is quite helpful. So let's just wait a second to complete that. So for everyone who was just kind of confused because Alan is so yellow today, it's just because the light is just that, right? I think it's perfect because it looks pretty cool. So it's just like you're standing out from the spaceship. So this is fine. And so no problem. Okay, Alan, so we're going to talk about few-shot learning in one sentence before you start. What is it and what can we actually expect from it?
So few-shot learning is the research into training machine learning models with very little data. So basically one of the big bottlenecks is that you always need a lot of training data to train your models. And with few-shot learning, we want to train models with very limited training data.
Okay, awesome. And you mentioned Flair. So I think part of the people who joined us today might have heard of Flair. Can you tell us a little bit more about for those who haven't heard of it yet?
Yeah, it's a deep learning framework for natural language processing. And it's basically designed mostly for the design goals of ease of use. So we want everybody to be able to use natural language processing in their applications. And it's also designed for state-of-the-artness, meaning that we always put the latest research into it so that the numbers, like the accuracy numbers that we get out of Flair are always the best or almost the best.
Cool. And it's open source, right?
It's very much open source and very much free to use. Yes.
That sounds like a good idea anyway, so to make it publicly available for everyone. I like that. So looking at the poll, I think I'm going to close that now. Let's see what the answers were. So we have, let you see the results. So 26% data scientists, so the majority is still, software engineering, software architects, together 26% as well. So 50% share, right? Business, we have some people from business here as well, and others, a lot of from others. I think I'm not going to ask the right questions here. Maybe you can help me just put it in the chat window. That would be awesome. and that would be helpful for me a little bit better to understand what kind of background you have, which is quite helpful. Coming back to what is your level of expertise in NLP? So we have a lot of people who are just beginners, which is also cool. Although it will be research focused, and you said a little bit more technical today, yes, which is good because we love models, so it's all fine. And we have experts, a guru. This time I think we have a guru here talking to us, so that's awesome. Yeah, so I think it's a good split looking at the knowledge which we can expect here. Okay, so I'm really excited to listen to what you have to tell us, and take the floor, Ellen. It's your show.
All right, thank you very much. So thanks again for inviting me and thanks for coming. So let me share my screen. So maybe as I'm sharing my screen, I'd like to ask everybody who has questions to basically just interrupt me with questions. I don't know exactly how we can do it, or maybe you can write it in the chat and Stefan can read it out. Yeah. Because it's always very helpful for me if people ask questions, because I don't like to talk for 1 hour straight. So it's always good. Okay, so the title of the talk is Few-Shot Learning for Natural Language Processing with TARS, which is a method that we developed. I'm Alan Akbik. I'm professor of computer science at the Institute of Machine Learning at the Institute of Computer Science at the Humboldt University zu Berlin. And to jump directly into the problem, so in natural language processing, there exists, of course, a multitude of tasks that we want to do. And in fact, last time that Stefan invited me, I gave a talk and I showed a bunch of demos on natural language processing things in action. And so I didn't want to repeat that, but I also wanted to maybe get on board some new people that are here. So I would like to show one demo to demo a little bit of what natural language processing tasks could be. And one of the most classic examples that we have is actually text classification. So in text classification, what we want to do is we have a piece of text and we want to train a model to predict labels for this text. And what these labels are depend on the use case that we are interested in. So for instance, here again, a very standard example is the task of sentiment analysis. So here we want to train a machine to distinguish the sentiment behind a text, right? So if somebody writes, I really like this movie because blah, 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 then we want the machine to be able to say, okay, this is positive sentiment. So this is like a positive attitude or positive sentiment that's in the text. And if somebody writes, I really hated this movie because blah, 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 then we want the machine to predict negative. So this is a binary text classification problem and a very, very standard example. But to get us all on board, I'd like to show this one demo. And so for this, I'll quickly switch the screen. To this. So I hope you can see it. Yeah, okay. So basically these are some models that I've trained. I've also showed this model last time, so I'm using a little bit different examples. And so let's assume, for instance, there's a lot of political discussion online and people write posts on things. And we want to train the machine to distinguish if people are being positive about certain subjects or negative about being certain subjects, right? And let's assume that somebody writes in a chat forum or somewhere, I support Amin, okay? And now we do a sentiment analysis over this text. And we want to know if this is a positive or a negative sentiment. And as we can see, we have two models, a transformer-based model and an RNN-based model. But actually in this talk, we only focus on the transformer model. We can see that the machine predicts positive for this piece of text, right? If instead I write, what could I write? Amin is not my preferred candidate, okay? Then I do another prediction. And now the machine or the model has predicted that this is of negative sentiment, right? And so this is basically the task. So if somebody writes, what could we write? I can't believe that Armin won. So what do you think, what sentiment this is? Is this positive sentiment or is this negative sentiment?
Good question. It's even difficult as if just reading it, right? I can't believe. So it might have kind of a bad connotation. It was not my dream. I didn't want him. I would say negative.
I can't believe I'm in one. So I'm also, it's very difficult because we don't have the tone, right? So we only see
Even
this
the
one
context is missing, right?
So I can tell you what the machine says. The machine says this is positive.
Could be positive, yes.
So it's a very difficult one. But if I add, I don't know, if I add smileys, so now we have positive like 85%. And if I add a smiley, now it's 99% positive. And I can try adding a sad smiley. And then it's still positive. Okay, so it doesn't work perfectly, but it works many times, okay? And so I wanted to also show a different model. So this is one I didn't show last time, this is emotion detection model. So on sentiment, we basically have two classes, positive or negative. But here's a model that can do 28 different emotions. It cannot do them very well, but I just wanted to show you that there are some models that have more than just two classes, right? So if I do emotion detection over this one, I get two emotions because this model can actually predict multiple emotions for one text. And the emotion model now is telling me it's surprise, which I guess is correct, and disapproval. So this is what the model thinks is happening here. And if I use the earlier examples, what was the earlier? I mean, was not my preferred candidate. If I use emotion detection here, I get neutral and disapproval. And if I write I support Armin, I get neutral, caring, and approval. So, okay, so it's not the best model in the world, but just to illustrate how there are different models that can do different types of classes, right? So let's go back to the talk. So hopefully that gets us kind of in the spirit of text classification. Okay, so the point essentially is that we can train different models to predict different things, and they can be two classes, they can be a single class, they can be multi-class. So a common example also is intent classification, where you, for instance, if you have your Amazon Alexa or something like this, and you give a command, then you're trying to classify the overall intent. Like play music, turn on the light, set the alarm, and you might actually have hundreds of different intent classes, right? And so this is typically modeled as a supervised learning problem. So, and supervised learning essentially has, as I mentioned in the beginning, has these problems that we have, that we require very large amounts of training data, and you require these training data for each class, for each domain that you're interested in, and each language. And to give you guys some feeling of like training data sizes, I want to show you the sizes that I used to train these two models. So the sentiment model that I just showed you guys had about 300,000 examples for two classes. And this, I graded this data set by joining many different sentiment analysis data sets. This emotions data set is called Go Emotions. It has 28 different classes, so 28 different emotions. And the number of examples is 50,000. And while the sentiment analysis model is actually pretty strong enough that we include it in Flair, the emotions model actually makes a lot of mistakes. Okay, so even though 50,000 examples sounds like a lot, if you have 28 classes, actually not so much. And it's, of course, emotion is a very difficult problem. All right. So what are the challenges? So from a practical perspective, the challenges are that training data is often not available, and it's actually quite expensive to produce. And I can tell you also from having worked in the industry for a long time, I can tell you that having access to training data is typically the main bottleneck in most use cases. So we can basically do everything that we want to if we have the training data. If we don't have the training data, there's almost nothing that we can do. So this is for industry and also a very interesting problem. From a research perspective, it's also very interesting because we might ask the question, why? As in, why do we actually require so many training examples, right? So because we know that humans can learn from few examples, right? So let's go back to this example of trying to distinguish whether a text is positive or negative, right? So if we train the machine, we require 300,000 examples or something like this. But if we wanted to have a human annotate this type of information in text, we would hire a human, we would explain to the human, okay, if the text is positive, you have to write it's positive, and if it's negative, you have to do negative. And maybe you can show the human like a few examples, like this is an example of positive, and this is an example of negative. But I would say probably for most humans, you would have to show them like 5 examples, and they would still do a better job than a machine that has seen 300,000 examples. So it's obviously possible to learn from few examples. And if it's possible for a human to learn it, maybe we can make it possible for a machine to learn from few examples, right? And so this is essentially also the topic of this talk and the topic of this research in few-shot and zero-shot learning. So essentially the goal is that we want to create models that perform NLP tasks with no training data or nearly no training data. And so to distinguish, so when we look at few-shot learning, essentially we're talking about, we want to show the machine 1 to 10 examples, and we expect the machine after 1 example or after 10 examples to do a good job at doing the classification. If we go into zero-shot classification, it's actually even more extreme. We don't want to show the machine any examples, and we still expect the machine to do a good job, right? And connected to all of this is this idea, it's a little bit connected to all of this, is this idea of continual learning. So if you have a model that can learn new things with very few training examples, then you could imagine having a single machine learning model that would learn over time, just like a human, you know, like a human picks up new tasks. This model would sequentially, through the lifetime of this model, learn more and more tasks without forgetting the old tasks, right? So it would learn sentiment classification, then it would learn something else, and it would learn something else. And so we would have one model that picks up more and more skills as it goes through its lifetime, okay? And so these 3 things are things that we think are really cool, and we would like our machine learning models to be able to do. And so this is also what this talk is about. So with this talk, I present the Taurus method that can do all these 3 things, and I'd like to show you guys. And this was published by paper by Humboldt et al. So this is the whole team. So this was created in collaboration with researchers at Zalando, where I used to work before I came to university. And the mastermind of this whole thing is Kisha Loy, who's the first author, and who can answer all your questions about the approach, right? So now that we've done the problem statement, so we want to do few-shot learning, let's look at some baseline approaches. So how would we normally build a text classifier, and what are the limitations of this? Then we go into our own approach, the task-aware representations that can do the few-shot and the zero-shot and the continual learning. And then I give a summary and an outlook. Yeah. Okay, to start with the baseline approaches. So neural language modeling, I think a lot of you guys probably know this, is currently one of the main drivers of progress in NLP research. The main idea here is to make a prediction problem out of plain text. Using something called a masked language modeling objective. So essentially the idea is to sidestep the need to annotate data by using plain text, unlabeled text, and turning this into a prediction problem. And so to show you how this prediction problem looks like, so an example, let's say we have crawled the web and we got like 1 million sentences, and at some point there's this text, a mouse on the desk. So what we do with masked language modeling is we corrupt this text. So we remove certain words in this text randomly. So it becomes a on the desk. And then we train a large transformer architecture, typically a transformer architecture, to predict the missing words back in. Okay, so we want the model to be able to predict that the word that fills this blank is very likely to be the word mouse. Yeah? And this formulation of the problem has a lot of advantages because this is actually a very difficult language problem. If I asked a human to say, okay, fill in the words for a on the desk, this would be, the human would only guess, of course, but in order to guess intelligently, you have to understand what the words mean, what the word mouse means, or what different words mean, and you have to understand the whole text around it, what it means. So this is actually a very difficult learning task for which the machine, in order to solve it, has to understand certain basics about grammar and about semantics. But another big advantage, I mentioned this before, is that we have unlimited training data. So on the one hand, this problem is super difficult, But on the other hand, we can generate unlimited amounts of training data. And that means that the way research is currently going is that you gather as much data like this as you can, just plain text, you crawl the web, then you create the biggest transformer architecture that you can build, the biggest GPU cluster that you can afford, and then you train a huge language model over this in the hopes that on the way it learns about syntax and semantics by solving this simple task. And what this then gives you is a trained language model that has a certain amount of syntactic and semantic knowledge. So to a certain degree, it can kind of interpret text, what it means, right? And so for instance, what you can do with such a language model, you can use it to predict missing words, right? So there's a nice UI by Hugging Face, which are a big startup in terms of transformers, where you can enter a sentence just like the one that I had, a on the desk. And now you want to predict different missing words with this model. And so this is kind of a cherry-picked example, but this model that I tried here predicted book, note, file, lamp, and notebook to be likely words that could be on the desk. Yeah. And I think maybe many of you guys have seen the example that you can use a language model to generate text that sounds pretty good, right? And because this is a big research area, there are in fact a multitude of such models that other people have already trained and made available over the past years. So you don't actually need a GPU cluster. You can just use the model that somebody else trained. Yeah.
Can I quickly ask a question?
Yes.
So the machine is looking at a sentence, right? On a sentence level. So it's not a paragraph or something like that. They're looking always on a sentence level.
It doesn't have to be. So you can actually, you can partition the text any way you want. So it doesn't need to be a single sentence. It could also be a paragraph or basically as much as you can fit into the model.
Okay.
Right. Exactly. So these language models have now learned certain things about syntax and semantics, and they are available. So what happens? So let's say we want to train a text classifier with such a transformer language model. So we're going to use again the example of sentiment analysis, but this time it's not only 2 classes. For this image, we used 5 classes. So we have, let's say, very positive, positive, neutral, negative, and very negative. So you see that on the top, these five classes here. So now in order to build a text classifier using a language model, what we do is we input this text into a pre-trained transformer language model. And essentially, because this language model has already been trained, it gives us some sort of interpretation of the semantics of the sentence, right? And then we take the last hidden state of the output layer, which represents the semantics in the way that the transformer model interprets it. And we take this hidden state and we put it through a linear classifier to predict the distribution over the classes. Okay, so this is a linear layer that performs a mapping into the classes. And this linear layer is randomly initialized. So we have a transformer model that we've pre-trained, but in order to make it do what we want to do, we have to add a randomly initialized linear layer on top. And so since it's randomly initialized, it doesn't make any sense. And the transformer kind of makes sense, but it doesn't yet make sense for sentiment analysis. So in order to make all of this make sense, we have to train this entire architecture using training examples. And during training, what happens is that this randomly initialized linear layer is trained from scratch to have good weights. And the pre-trained language model is now fine-tuned specifically for the task of sentiment analysis. Okay? And so this is the absolute standard approach. This is also the approach that you should use if you want to build a text classifier. And this is also the approach that is behind the demos that I just showed. So we take a language model and we fine-tune it for the task that we want to do.
Another quick question, Alan, just if you go back for a second. Simone Grieser just had a comment on sentiment analysis. She said it's more of a comment than a question. Human emotions, what was the emotions part? Sorry, not sentiment. Human emotions are not positive or negative. There are shades in between. I think that's pretty much it. Is sentiment analysis still that kind of distinguishing between 2 things? So it's negative, neutral, and positive? Or are we already better in doing that and finding all those colors in between?
It is possible to train models that that do more nuanced distinctions. So the binary classification is, of course, the most simple one, right? So you just have two classes, either positive or negative. So this is not very advanced. The one that we use here in this image has 5 classes. So we say very positive, positive, neutral, a little bit negative, and very negative. But what is also possible, depending on the training data that you have available, is to train, for instance, a regression model. And a regression model would give you a value, like a numerical value on a scale between something and something, and tell you essentially how happy or how unhappy a person is. But of course, so this, from a machine learning perspective, it's possible to train this. From a data perspective, it's not super trivial to generate this kind of data because sentiment is subjective. And basically, so the way, for instance, they generated this emotions data set is by asking several people. So they gave each text to several people and they said, okay, what emotion do you see in this text? And they, of course, found that people gave very different answers, but if many people give the same answer, then you become more certain that this is really a text and is about this emotion, right? So, but yes, it is possible.
But it tells you also a little bit that a machine cannot be better as a human, because as a human, we also struggle sometimes in making sense of what we hear, right?
Yeah, I mean, also because it's just very subjective sometimes, right?
Yeah.
So we're trying to, when we generate this data, we're trying to get like something more objective in a sense. But of course, everybody interprets these things differently.
Sorry for the interruption.
No, I'm happy, very happy. Yeah, so anyway, so this is the standard architecture. That's the one that everybody should use. And it's also the first baseline that we compare against. So let's assume, though, to do a little bit more transfer learning, let's assume that we have already trained our sentiment model. Okay, and we trained it by fine-tuning a language model. And since our language model is fine-tuned now, it now has a heart. It's a language model with a heart. And the linear layer in activation also has a heart. The reason for this is that the language model has now not only seen language, it's now also seen sentiment data. So presumably there's more information now in this model than there was before. So if we want to train a second model, this time a model for topic detection. So in topic detection, for instance, we might want to detect topics like, let's say, newspaper articles. Do they belong to, are they sports articles? Are they business articles? Are they politics articles? Like this kind of thing. So let's say now we have a new goal and we want to train this new thing for topic detection. We basically have 2 options. Either we do exactly the same thing that we did on the last slide, where we take a language model and fine-tune it for this task, or because we already have a fine-tuned language model for sentiment analysis, one thing that we could do, I don't know if I recommend it, but we could reuse again this fine-tuned language model. So we could also use the language model with a heart as a starting position for learning the topic detection. Because again, presumably this language model with a heart has now more information. Okay? And so maybe a question to the audience. What about the linear layer in the activation with the heart? Can we also reuse this?
Hey, you're challenging my audience. That's awesome. Let's wait if you can either answer in the chat or raise your hand. So if you like, I give you the right to speak up. We have some comments here.
Mm-hmm.
On the chat. Can you see it, Alan?
Oh, can I? No, I can't actually. No, I can't see it.
Switch to the chat.
Or maybe if yeah.
Master just num classes. Nope.
No, that's correct. Yes, I see several no's. That is correct. So you cannot, in fact, reuse this layer because I don't know. Can you actually see my mouse?
Yeah, we can see your mouse.
Okay, so because the number of classes that we're trying to predict is different, so the output shape is different, but also the semantics of the classes is different, right? So basically, we can't, in fact, reuse this. So even if we do transfer learning from this model, We could reuse the fine-tuned language model if we wanted to, but we cannot reuse the linear layer because this one always has to be randomly initialized and trained from scratch because this is where the semantics of the target classes are. Okay? So this approach of transferring from one to the other is our second baseline. And this is actually the standard transfer learning scenario, I would say. Okay, so let's do a recap. So if we want to do a state-of-the-art text classification, what we're going to do is we're going to use a pre-trained language model that somebody else already trained, like BERT. Then we're going to put a linear classifier on top and fine-tune the whole stack on a task. It's actually super easy. However, there are a lot of limitations. So the first limitation is that the linear classifier always needs to be trained from scratch because it's specific to each task. Secondly, it generally requires large amounts of training data to not only train the linear classifier, but also to fine-tune the model for what we actually want to do. And finally, this type of approach is actually conceptually unable to do zero-shot classification. Because if you require training data, because without training data, nothing makes any sense. The layer is randomly initialized, the language model was trained for something else. So unless we have training data, we can't do anything. Yes.
So since you just put it in here, zero-shot classification, what for heaven's sake is zero-shot? Can you explain that?
Zero-shot is without any training data. So this is if you want to do sentiment, and let's say you want to do positive and negative sentiment, but you have no training data for this. And then you want to have a classifier that can do this.
Do you think that is near to human level learning?
I think so, yes. So, but I'm going to show this approach now how it works. And once you see it, you're going to be disappointed because it's actually super easy. So it's actually very easy, the approach, okay? So this brings us to task-aware sentence representation. So the approach that I actually want to present that can do all this stuff. It can do few-shot, it can do zero-shot, it can do continual learning. And I should have said this in the beginning because otherwise now people are disappointed because it's actually super easy, yeah? Okay, so how do we do it? So how do we normally do it? So the standard formulation in classification is a text goes in and we have, let's say, P classes. And for each class, we want to know, does it belong to this class or not? So 0, no, and 1, yes. Now we reformulate this into a matching task. So the formulation is a tuple goes in consisting of a task label and a text. And we want to know whether this task label is appropriate for this text, true or false. And that's the only thing that we want to know. So to illustrate this a little bit more, same architecture as before, just that on top you only have two outputs and one is true and the other one is false. So still a language model, still a linear layer, but true or false. And now the input is not only the text, the movie was great, but we input the text and the candidate label. So the movie was great and positive sentiment. And if the model now says true, then we know, okay, this positive sentiment is true for this text, the movie was great. And if the model outputs false, then we know, okay, it's not positive sentiment. Yeah. So the main question that our architecture has to answer is, do the text and the label actually match? And so as you can see, this one is independent essentially of the task, because you can also put in topic detection. Let's say the White House stated blah, 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 blah. And then you say topic politics. Then you put in again a text and a topic. And this thing doesn't, the only thing that it tells us is that this label is appropriate for this text, yes or no. Okay. And so this means that it becomes independent of the number of classes. It becomes independent of semantics of what the linear layer actually tells us. Because again, it's only a matching task between label and text, okay? So to show this in a bit more detail, so normally, let's say a training example is the movie was great and the label is positive. So what we have to do now for this task, we have to reformulate it. So we've reformulated this actually into two data points, yeah? And one is now the text, it's a bit strange, is positive sentiment separator symbol, the movie was great, and the label is true. Because this whole statement, positive sentiment, the movie was great, this is true. And we also generate a second data point. negative sentiment, which is the opposite class. The movie was great. And this whole doubled statement essentially is false because this is not negative sentiment. Okay? And so this gives us one long string essentially that encodes the fact that we want to match a label to a text. Okay? And so this now we put into the transformer. Just like before, just now we put this full string in, positive sentiment, separator, the movie was great. This goes to the transformer, which is seeing both things at the same time. And again, the transformer now has to make the distinction, is it true or false? And one of the things that's super important here now is that we actually have to rephrase the label as a natural language description. So before it was just a label or like a code or something like this. But now we have to rephrase it into an explanation because it's a language model. The language model can understand to a certain degree language. So if we say positive sentiment, then this description has semantics. Mm. And this is also, when I talked about in the beginning, like how do you train a human? It's not only training examples, you also explain the task. You say, you have to annotate positive sentiment in this text. So, and this is essentially what's happening here because we're now giving the model not only a training data item, but we're giving it a human language description of what it should do. Yeah? Mm-hmm. And this, of course, does multiply our training data by the number of classes. So now we have 2 classes. So for each data point, we generate 2. But if we have 10 classes, then for each data point, now we generate 10 data points in the training procedure. Yeah? So what are the advantages of this? So this means the entire stack is now independent of the number of classes in a task because it's always the same output, true or false. It enables the transfer of parameters, of all parameters between the tasks. So we can put anything we want in there. And we now, that's the most important thing, is we learn the semantics of classes, not only from examples, but also from the name of the labels. So if our model is very good at interpreting label names, it could potentially learn things for classes we've never seen before, right? And this essentially makes zero-shot classification possible. So I could just say, okay, and I've tried it, so I can have a trained model, and so I put something in that I've never seen in the training data. Let's say I put in neutral sentiment, and it's never seen an example for neutral sentiment, but maybe the language model understands what the word positive and what the word neutral means. And if it learns this matching, it can deal with new classes. Okay, so maybe just to check, so how much time do I have left?
Oh, a lot. Wonderful.
I have enough? Yeah, okay, good.
Yeah, no worries.
Okay, so let's evaluate how well this actually works. So we are interested in the zero-shot and the few-shot regimes, meaning we don't have so much training data or we have no training data. So we want to compare TARS against the baselines that I mentioned. We're kind of interested also in the effects of the semantic distance. So if, for instance, we learn topic classification, then a different topic classification, is that easier than learning two things that are completely different, right? And the question also for me is super important, or super interesting at least, is can we have a single TARS model that we can teach more and more things over time, just like a human learns more and more things, yeah? And so this is our training testing setup that we used in the paper. So we have 6 task data sets from question typing, sentiment analysis, and topic detection. So these are just different text classification tasks. And what we generally do is we train the matching logic on the source task with all the labeled examples. And then we fine tune the model only using very few training examples from the target task. So this is the task that we actually want to do. And then we measure on the target task. So essentially we give it like one example and we measure how well it does on the target task. Yeah? And like I mentioned, we compare against 2 baselines. One is just a normal classification setup, and one is a transfer learning setup, the second one that I mentioned earlier, where you take the language model with a heart and use it in a different one. Yeah? So now comes the big table. So maybe to explain this table a little bit. So we have these 4 boxes, and each of these boxes means that the matching logic was trained on one task, and it was then evaluated on a different task. And so in this case, for instance, it was trained on Yelp data, and it was then evaluated on Amazon data task. Yeah. And what you see here, this K, is the number of training examples that the method has seen. So K0 means it is zero shot, it has seen no training examples. And we show it in 1, we show it 2, we show it 4, until we go up to 100. And we always measure how well it does on the target language task. Okay?
Yes.
Then you see the baseline. So this is the standard approach that you should normally use. This is the standard transfer learning approach. And this is TARS. Okay, and so maybe to kind of directly jump to the results. So at 0, we know that the standard approaches cannot do 0, but TARS can do 0. So at 0, we always outperform everybody. So that's easy. But we notice that actually in most of these data sets, for few examples, we do really well. So I don't know, if we look at this one, for instance, only one example, or let's say 2 examples, and it's already better than most of the related work, right? So these are different tasks. So if we look at here, we're better until we reach 10 examples, and then 100, the baseline approach takes over. So this is an approach really if you don't have so much training data, right?
A short question again. Looking at the first quadrant of the first table, basically Yelp, looking at the numbers, these are percentages, right?
These are F scores. Or
F scores,
yeah,
okay. Okay, thank you.
Yes, so 100 would be the best, and 0 is the worst, yes. So this is in domain. So in domain, we generally do very well, and we outperform most of the baselines. Now, cross domain means that there's a large semantic distance. So for instance, we train on topic classification, and then we evaluate on a question type. Here it still does okay, but if we train on sentiment and then take it over to topic, it's actually not so good. So here actually just training directly on topic is a better idea because the distance between sentiment and topic is too large. So essentially it's learning the matching logic on sentiment. It's trying to apply it to topic detection and it just doesn't work. Yeah? But even here where we perform worse, we still very much outperform the standard transfer learning approach. Yeah? So it's still better than the normal transfer learning if the semantic distance is very big. Yeah? Okay, and so now, yeah.
Sorry if I just ask that again. If it's about domains, it's about knowledge and transferring knowledge from one to another domain. Can you give an example of what kind of sentence that might be? Would be?
So yeah, so essentially what happens here, if we train on sentiment, the model is essentially learning how to match statements to labels to text is only based on, well, essentially two labels, positive sentiment and negative sentiment. And so it's only learning essentially how to match positive sentiment to a text and negative sentiment to a text. And if we go to topics, then we want to have topic politics, a topic business. And so the problem is that the way the semantics of the labels are too far apart. So it's too difficult for the model to transfer the semantics that is learned from one label to another one, right? But in a sense, I would say this is actually a flawed experiment because we are learning the matching logic only on one task. And really what we want to do is learn the matching logic. So we want to teach the model to interpret labels, many different labels as possible, right? And so this is kind of what brings us to this experiment. So I personally think it's very cool, so bear with me. So what we're doing here, so this is like a timeline, okay? So we're training this model to do different things. So first we're training to do a sentiment analysis on Amazon, then sentiment analysis on Yelp, then topic detection on Wikipedia, topic detection on news, and then question classification. And then this is like one meta epoch. And then we actually teach it the same 5 tasks again. So, and at the end of teaching at each task, we evaluate how well it does on all of the 5 tasks. So blue bar is Amazon, red bar is Yelp, okay? And to show you this, so after we taught it to do Amazon, the blue bar is the highest because the blue bar is Amazon, but Yelp is very similar. So it also has pretty high bar. And the other tasks, they exist because the model can still do 0 shot on these tasks. So it's never seen DBP, also never seen Yelp, but it can still do something with this data, even though it's never seen it. Yeah. So now we take this exact same model. Now we teach it Yelp. And now what you can see is that Yelp is now bigger. Red is Yelp. And the other ones have also kind of improved a little bit. Yeah?
Mm-hmm.
Then now we teach it DBpedia. So DBpedia, what you see now, the yellow bar goes straight up because now we taught it how to do DBpedia. It's no longer doing zero shot. It hasn't really forgotten the other things. And it's also improved on AG News on Track. So now we train another one. And so the green bar now is pulled up, AG News is now up, and Track, then the question, the orange bar is also pulled up. So this is after one meta epoch. It has learned a lot of things. It has a little bit forgotten the first ones, but not so much. But it's still doing pretty well. And so now we do another meta epoch. And what happens is that it doesn't learn so much new stuff anymore, but it's still going up a little bit. So now at the end of these two meta epochs, there's a single model that can now do these 5 tasks, okay? And so this is kind of a model that learns to do more and more things over time, which I personally think is super cool. Okay, so to bring us to the key insights, the Taurus model outperforms the baselines on most few-shot scenarios. Taurus can actually learn many tasks in sequence, as we've seen. But of course, the semantic distance between the source and the target task is important. And since we double and triple our training data, we require separate 4 passes to the model for each candidate label. Yeah? Taurus, of course, as always, is released as part of the Flair framework, so you can already try it out. And in fact, we released a Taurus model that was trained to already do 9 tasks, so it's a pretty powerful model. And we're training bigger ones. We're going to train one that can do like 30 tasks. So we have a lot of things in store. This model has very surprisingly strong zero-shot capabilities, and I very much recommend to you guys to try it out if you have use cases where you don't have much training data, or you have use cases where the classes that you want to classify are very imbalanced. I think this approach could also do very well there. That kind of brings us to the end. So we're doing a lot of things with Taurus. We're building on this. We're bringing it to different NLP tasks like sequence labeling and relation extraction. We're doing like this idea of training it for like so many different tasks. And of course, making it multilingual. Another thing that I wanted to also tell you guys is that we are looking into few-shot learning for language modeling itself as well. So essentially, I mentioned this in the beginning. So currently we train language models on larger and larger GPU clusters and data sets. But the question is, can we learn language models also with not so much data, right? And in fact, there's a little statistics that I want to give you as a final statistic. GPT-3, which is the biggest model that exists, was trained over 500 billion tokens of text. And there are estimations that the average North American child hears about 5 million words per year. So as you can see, there's a gigantic discrepancy here. And of course, the child still speaks better language than GPT-3. Hopefully. So it is, again, somehow it is possible. And so for this, we're starting a big research group in my department. It's a DFG-funded project. And we have 6 years' time to investigate this big question. And I'm very much looking forward to doing this. So thank you very much.
So first of all, congrats to the research funding. That sounds awesome. I invited actually a few people just to join the panel. Stuff is, Zinab, you might have seen that I allowed you now to speak up. I saw you had questions in the Q&A section. Thanks for just putting the questions in there. Staffis, would you like to just begin?
Yes, of course. Hello to everyone. Alan, congratulations on the presentation. It was very beautiful. I added 3 questions. We don't have to answer them all. Can I ask them?
Yes. Just
right.
go ahead with the first one.
First of all, it was a very great idea. I liked it a lot because how you change a little how we formulate the supervised learning problem, where we add also information from the task in the input sample as a text description also. You saw some examples. when you show us this, I asked to myself, what happens when we create this training data, when we synthesize this training data? Because I would like first to tell us some things about how when we are creating this data set, a multitask data set, if we have some challenges for the negative sampling, because there might be some multiple combinations, you know, don't you need also some negative examples? For example, this is the first question.
Would you like to answer it directly, Alan?
Yeah, so we absolutely. So we do sample negative. So we create negative examples as well. Essentially, I showed it on this one slide. So essentially, we can go back actually. So here, so if we have one training data item, the movie was great and the label is positive, we create two examples. One is a positive example that says it's positive sentiment. So this is essentially a match. And we create a second data point that is a negative sentiment, but this is labeled as false, meaning that this is not a match. So this one should be a match and this one should not be a match. And so this is the way that we generate the negative examples by essentially interpreting all the ones, the classes that are labels that are not seen for this data point as negatives.
This is great, but you know, it came to my mind what happens in multi-classes. You know, 10 classes, you have to do a lot of negative sampling, etc. Maybe there was a challenge there, or I don't know. I'm just asking this.
No, you're right. You're absolutely right. So this is, so in the implementation, we actually implemented a technique called hard negative mining, where we essentially don't always sample all the negatives because this would be too much data, but only sample. So basically we say, okay, maximum 4 data points, sample 4 negatives per data point, but we sample them in such a way that they're difficult. So because then the machine can learn, the matching logic can learn better if we sample more difficult labels. And so there is, so we have this in the implementation.
Nice, great.
I started. Can you stay here for a while? We have 2 more questions. I just pass on to the next one. We can come back to the other questions as well.
Yes, of course,
Yeah,
Steve.
fine.
Yes.
Sinab, you actually have a chance to talk as well. You're just unmuted for a moment, so if you unmute yourself, you can ask the questions.
Hi, can you hear me?
Let's try it again.
Hello?
Yeah, better now. That's better.
Okay. First of all, I want to thank you for this wonderful presentation. It is very informative and, to be honest, it's smart, very smart, and yet it's a little bit hard for me to perceive the concept. My question is about the way the label can be rephrased. It can be rephrased into any phrase as long as it can express the positive or the negative sentiment, or there is a specific way to rephrase it. And the few data that we are using to train the model, it can be a very specific data. We have to be careful to choose the data, or any data can be used to train the model.
Yeah, great question. So, so with the task label, essentially, it needs to be human language and it needs to have the semantics of the task that we're interested in. So it needs to be, it doesn't need to be, for instance, positive sentiment. You could also say the sentiment is positive or the feeling is one of happiness. So somehow it needs to describe in human language the semantics of the target class. Now, one of the things that we didn't do, in this paper at least, is to evaluate what is actually the impact of how I formulated, right? So we basically, we just took the first one that came into our head. So we just said, yeah, it's positive sentiment. Yeah? But we never tried what happens if we write happy sentiment or something like this, right? So I think there's a lot more study that could be done if this somehow has an effect on the way the model learns to interpret these labels, right? In terms of the training data, I would say generally, the more diverse the training data is, the better. So if you have more diverse semantics, probably it would work better. Yeah.
Thanks, Tina.
Okay, thank you. Thank you. Thank you.
Thank you. Xavier, you also have raised the question, so I would like to give you a chance to speak up.
Thank you. My question is like, at training, you say that you can limit the data points to 4, but what happens at different time? The task label, you have to pass all the number of labels times the number of example, right?
Yep. So that is the big disadvantage of the approach, is that for each candidate, you have to do a separate, do I have it here? Yeah, so you have to do a separate pass through the model. I had it on the final slide. So this is essentially the big conceptual disadvantage of this approach. In terms of runtime, you just have to do multiple forward passes through the model. There are some ways to speed this up. There was a paper at NIPS in, I think this year or last year, last year, on architectures for this type of matching. If you don't want to do the self-attention through all the layers, that there are certain things that you can do to speed it up. But absolutely, you have to do multiple forward passes.
Yeah, thank you. Thank you for the question again, Xavier. I also would like to just allow Craig. You joined us as well. You guys haven't met before, but Craig is actually a professor of NLP as well. So introducing Alan, introducing Craig. You should meet at some time. Craig, what was your question?
Yes, so first of all, I would like to thank Alan for the great and clear presentation and very interesting approach. I like simple approaches that work like this one. And one of my questions that I guess partly has been answered is concerns if TARS can scale to really larger kind of problems like the MES thesaurus with 28,000 classes or even bigger ones. So I guess there is a problem in the inference time, but also a training time. Is there also a problem?
Yeah, I mean, so we haven't tried it on problems like this. It would be, I think for me, it would be super interesting to try stuff like this. But we haven't done any experiments here. So like I said, so for training, we do have ways of limiting the samples that we sample for each class. But if you have, how many classes you said, 20,000 or?
Yes, 30,000 in this problem. Medical labels.
The medical, yes. So you probably need, so I mean, you could still probably try this approach, but you would need some extra layer, some pre-selection, or you would some speed up arithmetically, so something. So you cannot try this approach the way it's done in the paper. You need something extra.
Okay, and if I can follow up question concerns this idea that maybe we could obtain a few shots of noisy labels or even many shots of noisy labels, in some sense a bit cheap. For example, we could spend some money on crowdsourcing, or there are some other ways to get weak labels, let's say. So I was wondering if, what is your view on weakly supervised learning, if this can be an interesting alternative?
It's an interesting alternative. So my personal feeling is that, so I've made like very mixed experiences with crowdsourcing. So I've also one positive, but also a negative experience. So my feeling is that if we have a method that can learn from few training examples, we should just give it really good training examples. So we should give it 5 really good training examples, and then just use really like from experts, the training examples.
Okay, thanks again, Alan. It was really a pleasure to watch.
Thanks, Craig, for your questions as well. I have a question here from Mira. She was asking, is TARS robust when we have a different distribution of test and training samples?
I hope so. So I think so. I guess the easiest way to find out if it's robust for your problem is to try it out in Flair. So it is already part of the last release. So you could, there's a tutorial online with instructions on how to use it. So I would actually generally be very interested to hear people's experiences with TARS, because one of the reasons we put it on there is so that people use it and experiment for different types of problems. So it would be very interesting to hear how well it works. But I think it should be robust.
That's good. Before Stapis can ask his next question, a quick organizational thing. You mentioned many times the paper you actually published. Do you have a link anywhere in the presentation to the paper?
The one, so it was listed, and again, it's actually a good opportunity to once again point out who the first author of this paper is. Where is it? So this is, so there's a link here.
Yeah, okay.
And again, so really the mastermind behind all of this is Kishaloy, who came up with this approach and implemented it and did all the experiments. So he's a very good person to speak to about zero-shot learning and few-shot learning.
Cool. Are all 4 people based in Berlin at the moment, or just doing remote work somehow?
We are working remotely, but all in Berlin. So.
Got it. Okay. So Corona dependent. Stapis, I would allow you to the next question again.
Yes, thank you, Stephen. Thank you. Okay, my next question, it has to do a little about the tasks that this architecture can learn. What happens, of course, the output is binary, right? And the input is just a textual description as a combination of the data, the information, and the task. What happens in other problems, like, you know, from natural language generative models, for example, where we generate text for machine translation, maybe, or summarization, or even, again, classification, but sequence classification, like part of speech, name and recognition. How we could somehow formulate, stick in the same formulation and describe, you know, the input label stuff in a single text for the input model, for inputting the model.
Yes, I mean, that's a very interesting approach. And this is an approach that I think it's called text-to-text transformer. I do have to look it up, but I think it was from Google. And they did such an approach where you essentially put in, it's kind of similar. You put it into like a sequence-to-sequence model, and you put in the text and you put in like a command, what you want to happen with this text. And the command would be something like translate into German or something like this, right? Or I don't know what else there is, but there were like some commands, yeah? And so this, I think it is kind of like this approach that you are saying. So it's, I can look it up. So it's, I think it's called text-to-text transformer.
You can pass it on to me, so I can pass it on to Stapis. That would be good. Fantastic. Olga, you have a question as well?
Yes, thank you. I'm not sure I understood well, but you use for the label of the of your text, you still have, it still has to be a human that enters that, right?
Yes.
So it doesn't say like, it doesn't find out a new topic by itself.
No, so there is still supervision. So there is, so this part, no? So this part of, almost there. So this label positive, turning this into a text description is human work. So sometimes the labels are already kind of like human readable. So even positive could be seen, okay, this is kind of human readable. But sometimes the labels are just like a code, like a 0 or 1 or some weird label. And they need to be humanly rephrased into something that carries semantics. But this is still not so much work, right? Because normally you don't have so many classes, so you just sit down and write some labels.
I think the point of asking the labeling question is a good one, which brings me just a reminder and a note, a side note. We will have a talk about data labeling and especially in those kind of models. So what's the future of data labeling and how does it work? February the 3rd, so it's just in a few days again. And from the experts, basically from Yandex, the biggest search machine in the Russian world. We built a company of its own, Taloka, which is just focused on data labeling. And so these questions are quite interesting to discuss. Maybe you can join as well, Ellen. Would be interesting to have you on board, just to see what's the future here. Data labeling, and as you mentioned in the beginning, is a huge part of the whole model building, right? So the data problem itself. So this is trying to figure out a way to reduce the workload by costs, as you said. And does it solve a problem on the quality side? That was a basic question. We will see if we can answer that. And so I just invite everyone else, also you again, to join us February the 3rd. Thanks, Olga, for bringing up that question.
Thank you very much.
I would like Stano to invite you to just ask your question as well. Can you hear us?
Stephen, are you talking to me?
No, yeah, in a second, you will have the closing question. That's a fantastic thing, Shavid. I know, Stano, how did you came up with the idea about this question? Stano, are you here? Can you can ask the question now directly if you like. Maybe it's to mute. So how did you come up with the idea? Let's ask the question directly. Well, why did you come up with that idea to us together with a team, and why was it just brought up?
So this idea. So I think there was a very strong motivation to find a solution for this type of problem, because so this is, like I said, for Zalando, where I used to work, and there are, in fact, there are a lot of problems that we wanted to solve. And I was in the natural language processing team in the company. And so basically the dynamic was that teams would come to us and say, okay, we have this and we want to do that, okay? And so this happened a lot, actually. So we had a lot of different teams because it's a very big company. And we were like the natural language processing team. So a lot of teams came to us almost every day, feels like, and had the idea. For our product, we need blah. And then, can you do this, or can we do this? And then the answer for me was always, yes, but do you have training data? So it was always about the training data. So, and very often, of course, there was no training data. And then it was, of course, you can now hire like a professional company, or you can try to label training data yourself. But very often you're not directly in the project phase where you want to commit resources and time and generate 100,000 training examples, because it's very expensive, right? And takes a lot of time. So very often what people want to do is have like a quick prototype and see how well it works. And I think because this is just something that was our daily thing, it just gave a very strong motivation to look into zero-shot learning.
Mm-hmm. Okay, thank you. Shafis, now it's up to you for the last question. Thanks for all the questions. I like that. That's awesome.
Thank you, Stephen, once more. Okay, my last question was about the slide. You saw us a slide, Alan, where you trained the model sequentially, continual learning in various data sets. And yes, if you can go there, it will be perfect. Perfect. I want to know how exactly you did that, because okay, Amazon has a specific data set with some text. It has some distribution there. Okay, specific. You train the model, perfect. Afterward, when you retrain the model or continue the training in different data sets, did you include in the data set also some examples from previous knowledge? I've seen in the past a problem that is known as catastrophic forgetting catastrophic problem. I think it's called somehow like that, where you train a model on a new data set. You have to include also some other data, some some examples from other data, from the previous data sets, so that the model don't forget what already has learned, because the new data set might has different distributions, etc. And we see here that the model continues to perform well on every. At the end, the model is very good. For example, how you did that?
Yes, so it's a great question. So we were precisely interested in this, and so we actually did not include any old examples. So every time we trained it on the new task, we only trained it on this task, and we were actually interested in measuring how much it forgets of the old task. So I think it's probably like the main motivation for this experiment was to see if old tasks then go down if we learn a new task. And it seems that there is some forgetting happening. You can see this a little bit. So you can see here the sentiment goes down and then it goes up again. So, but it doesn't go down very much. So it's actually, for the most part, it's doing quite well in remembering things. However, I should also point out that this is only one experiment, right? So, I mean, because there's so many experiments that one could possibly do with this kind of thing, right? So like you said, we could use this idea and mix in old data points, or we don't even have to train it in sequence really, right? So we could just make one data set out of everything and just train it over everything at the same time. There's really nothing stopping us from doing it because the model, it makes no difference to the model, right? So this was one experiment with 5 data sets that we saw twice, but there are so many things that one could try here.
Okay, thank you a lot.
So basically, I think we had all questions answered, which is just fantastic. Again, a big thank you for everyone who attended today. I loved your questions as always. That was quite informative. I think many questions still are in my mind. The domain problem you mentioned, the memory stuff you just started to begin a little bit talking about. I think there's a lot of we can have in the follow-up in some months to go. It's probably enough stuff again to talk about. Alan, I would like to say thank you again for being part of the show, maybe running the show this evening. And thank you for taking the time to explain all that to a quite interested audience. Thank you.
Thank you very much for inviting me, and thank you for the very interesting questions.
So I wish everyone a nice evening. Thanks for joining us, and hopefully we can see each other maybe tomorrow. Tomorrow we will talk about ethics, AI and ethics, which is also quite interesting stuff. Something a little bit about practical AI and ethics as well. Stop hate speech, which is the cool stuff. So very practical as well. And yes, have a nice evening. And still, as we are in Corona times, stay safe, please. And I hope we can see each other in a healthy situation. Bye again and say hello.
Thank you. Bye-bye.